Okay, again, we start on page 28 today. A couple of things happening today. First, the quiz is wrapping up as we speak, and project 4 is due today, so put it in the folders if it's not there already. I do take quizzes late. There are lateness penalties, but hopefully they're in the folders at this moment. Today we're back in chapter 1. We're going to review inverse functions and log functions in preparation for next class where we talk about the derivatives of inverse functions and log functions. One other thing, project number 5 is going to be assigned on Monday, which means I should probably print project number 5 before Monday. So project 5 is assigned Monday, and it will be due October 29th, whenever that is. Any questions on the calendar? Okay, one other announcement before we dive in on page 28. The Math Club, after a temporary hiatus, is coming back. We're going to start up meeting this coming Monday and we'll meet every Monday from noon until 12:50 right here in this room. What is the Math Club going to do? I don't know. We'll decide on Monday what we're going to do, but we'll hopefully take a look at some interesting and challenging math problems, calculus and otherwise. We might play some math games and think about some math puzzles and just hang out with people that, as if this wasn't enough math you were doing, would like to do a little bit more. So no pressure. Bring your lunch if you're available and interested. So right here, this coming Monday is the start. Good? I am advising. Yeah. Okay. So on page 28, let's see. So a few topics that are in the book, and you'll see them in the homework. We're not going to do anything about them, but this section does cover shifting and stretching of functions, symmetry of functions. Even and odd is a concept that's easy, but it's also easy to forget. So just have a look in the book to remind yourself of what those things mean, and also composition of functions, which we've already spent a bunch of time on in preparation for the chain rule. And the goal for today is to think about whatever the inverse is of an exponential function. And what's the name that we give to the thing that is the inverse of an exponential function? Is a logarithmic function. So that's the heart of today. But before we go to the heart of today, let's just talk a little bit about inverse functions in general, more generally than exponentials and logs. So here's a question. It says f of x is x over x plus 1. And then I'd like you guys to try to calculate with your neighbors a formula for the inverse function. This is a multiple choice question, so it's not 5 different questions, okay? So find the inverse of that function, and hopefully it'll be one of those choices. And I'm guessing that there's probably at least one person at each table who doesn't quite know how to start, and somebody else at the table who does. So figure out who you are, and then ask for help or give help, and see if you guys can come to an inverse function rule here. All right, so I don't expect many groups, if any, are at the end, but let's at least make sure that we're all headed in the same direction. So I heard a few folks talk about this is the kind of problem where you have to switch the x and the y, right? So first thing I did is I just brought a y into the problem and then swapped all the x's and the y's. And the goal is to solve for what letter? Solve for y, that's the goal. So in my case, I cross multiplied and I distributed, and then I get to this kind of funny looking equation. And it's easy to solve for y if you have the technique, but if you don't have the technique, it could be darn impossible. What's the technique to solve that funny looking equation for y? Multiply by the reciprocal. Yeah, we need all the terms with y in them to be on one side and all the terms without to be on the other. And that's the key for a lot of these kinds of problems. Tony? You could factor x out. That would bring you right back to the previous one. I think that distributing is going to head us somewhere good, but let's do what Ernie suggests here, and let's bring the xy term over to the right-hand side. And the whole point of putting all the y terms on one side and everything without on the other is what can you do on the right-hand side now? You can now factor y out. You can factor that y out of both terms only because we put all the y terms on one side and everything without on the other. And what that does is it takes the previous equation, which had a couple of y's in it, and gives you an equation which has only a single y in it. And that's good. So now what do we do? I think we heard Todd say it. Good. So we divide both sides by 1 minus x, and we have solved for y. What's that? It's always c. You should have just guessed c from the beginning. And then just to be clear, instead of y, what would be a more descriptive name for this function? That's f inverse of x. F inverse of x. Any questions on that one? It's okay. So again, I feel like a lot of folks remember this idea of swapping x and y and then solve for y, but sometimes the algebra can be difficult. This is a pretty common technique for finding inverse functions. Get all the y terms on one side, everything without on the other. Okay, number 3. All right, so now we'll talk about like why we actually are interested in inverse functions is we're thinking about log functions. And so just a real quick refresher, y equals log base b of x means something very specific. It means something raised to the something is equal to a third something. Can you guys fill in those 3 boxes? Your choices are y and b and x in some order. What does it mean to say log base b of x is equal to y? And if you feel like you've gotten that written down correctly, write down something analogous for parts B and C. Check in with your neighbors on that first one, and then see if you can agree on B and C. Okay, are we okay with the recollection of what those funny symbols mean? Right. So every log equation has some corresponding exponential equation. And there are a couple of bases that are so important to us that we just give them special designation. Base 10. Anybody know what the name of that log is? Yeah, it is just log in terms of how we write it, but it has a special name. Yeah, it's the common log. Okay, so that's the one in part B. So if you don't see a number down there where the base should be, it's assumed to be 10. And then in part C, what's the base? E. And what's the name of that kind of log? The natural log. So we have the natural log, we have the common log. We're going to be using the natural log pretty much exclusively because we've already seen that the derivative of e to the x is e to the x. But the derivative of a to the x is slightly more complicated, right? I had to stick on an ln of a at the end. Okay, in part 4, I'm going to ask us to do a couple of things. So we're going to type this in, but don't do it just yet. Log of 800, I'd like us to have a sense of what that should be. When I first saw logs, they were quite mysterious. I was able to type it into the calculator and I could do some problems, but I didn't have any sense of how to estimate log of 800 without the calculator. But let's just give this guy a name and see if we can figure out how it translates. So I'm going to call it y. You guys then can write some exponential thing based on this. What to the what equals what? 10 to the y is 800. Right, that's the same translation that you guys just did on the previous page. Okay, the value of y that's supposed to go up there is some decimal, but can you guys hold up the number of fingers and trap y between 2 consecutive integers? I mean, is it between 0 and 1? Is it between 4 and 5? What is y between to make this equation true? We got 2 hands, so hold up 2. What is it trapped between? All right, so if y is 2, your 10 squared is 100, that's too small. 10 cubed is 1,000, that's too big. So definitely this answer is some number between 2 and 3. Yes? Okay. It feels like it's going to be closer to which one? Yeah, I mean 100 versus 1,000 and 800 is a lot closer. Now, it's not a linear thing, so you can't just always say, but 800 is pretty darn close to 1,000. So I'm expecting something near 3, and so on the calculator. The calculator can give us a very good decimal approximation here. And on the left-hand side, you'll see there's 2 log buttons. Log, which is the common log, base 10, and ln. In our case, we want log of 800. And we said probably something close to, but a little less than 3. Good? All right, so from the calculator, log of 800 is about 2.9. All right, next question asks for the relationship between f of x is e to the x and g of x is ln of x. What are those two functions called with respect to each other? They are inverses. These two functions are inverses of each other. They undo each other. So we'll write that, and then we'll talk a little bit about what that means graphically. So 6 asks for the relationship between the graphs of two functions that are inverses. There's a certain kind of symmetry that two graphs have when they're inverses. What are they symmetric with respect to? Yeah. Okay, so I imagine that some folks have in their minds that they're symmetric with respect to that. So let's write down the equation, y equals x. So what we're going to do, we're going to skip 7, which asks you to basically just take a graph and draw the thing that is symmetric with respect to the line y equals x. We'll basically do it in number 8 with a function that we actually care about. So it says sketch e to the x and sketch y equals ln of x. And what I'd like us to do, I know you guys have a sense of the graph of e to the x. Is exponential growth or decay? Right, so we know we're expecting something like that, but I want to be a little more precise than that. So how about we just make a quick table and we'll use the calculator x and then y is equal to e to the x, and I'm going to pick 3 x's. We'll say -4 and 0 and 2. So just to the nearest tenth, you can grab these things from the calculator and plot 3 points. Okay, what do we get for e to the -4? 0.02? Is that right? Okay, so I guess nearest tenth isn't going to be good enough for that one, so we'll say 0.2 on that one. E to the 0, it's 1, right, that's easy. E to the 2, 7.4. Good, so you can plot 3 points, and then we can connect them to make the graph of e to the x. Which one of these points have I done the poorest job of approximating? Which one? The 0.02, right? I mean, like the 0.02 is basically where, basically on the x-axis. I'm exaggerating it here so we can see it, but you get the idea that this guy gets close to the x-axis very quickly, far more quickly than if I just kind of freehand a general exponential function. Okay, so this is the graph of y equals e to the x. Fair enough. And then some folks remember that if you graph the inverse, it's symmetric with respect to the line y equals x. Well, let's see if we buy that by just plotting a few more points. Does anybody know the first x that I want to pick for the graph of y equals ln of x? I want to pick 0.02. That's exactly right. I want to pick the y that I got over here. And if you understand this idea of inverses, then you should be able to fill in the second column there without any work. But it's okay to just type in ln of 0.02. What is ln of 0.02, or maybe better, the actual number that we had there? -3.9 and change. So really, what should it be? Should be -4. And ln of what's the next x value I want? I want to pick 1 for the x, and then how much is ln of 1 is 0. And then the last x is 7.4 and 2. So go ahead and plot those points. Okay, and so we get this graph of the ln function, and you can see it gets really, really close to the x-axis. Sorry, it gets really close to the y-axis, but never hits it, in the same way that our graph here in black gets really close to the x-axis, but never hits it. Right, so that's it. So just a couple of observations about the graph of y equals ln of x. So first of all, we see that what happens when you go from a function to its inverse is the x and y coordinates swap, which actually makes an awful lot of sense, because when we did the very first problem today, and I said to find the inverse of this function right here, what did you do as your first step? You swapped the x and the y. So of course the x and the y's swap. And then in terms of the symmetry here, so I could draw the line y equals x, and we'll go ahead and draw it right through here. And we'll try again. Oh, that's not bad. And you can see the symmetry, right? They're kind of mirror images over that diagonal line. All right, so because e to the x hits the point 0, 1, ln of x hits the point 1, 0. There's not a lot of nice points on the graph of y equals ln of x, but there's one that I'd like you to be aware of. ln of x hits the point 1, 0. And the other thing about ln, is it concave up or concave down? Always concave down, in the same way that e to the x was always concave up. Flips over. Is it increasing or decreasing? It's increasing. And how high does it get? Because it sure feels like it's growing real slow. I mean, like to get from you know, like the x-axis up to 2, we had to go all the way out to 7.4. If I wanted to get, so could you guys just type in, for example, what if I put one more point in this table? What if I put x equals, oh, I don't know, 500? Can somebody find ln of 500 on how much? Yeah, so it's pretty small. How much is ln of 500? 6.2. So I'm going to have a hard time plotting this, but I'm hoping you get the idea here that if you go out to 500, which is maybe outside the building, how high are we? 6.2, right? And to get to 7.2, you got to walk, you know, like you'd be down in, I don't know, might probably still be in Massachusetts, but maybe, I don't know. I mean, like you really have to go far to rise. So how high does it get? I mean, like, does it level off at, you know, maybe it doesn't ever get past 10 or 100 or something like that? How high does it get? It gets up to infinity. It gets up to infinity. This thing does not level off anywhere. It is really slow, but it gets higher than any number you can name. If you say, hey, Ian, I want it to get up to e to the 100th, I want it to get up to 100. I say, no problem. If you want it to get up to 100, I can tell you exactly what it should be. If you were to find ln of e to the 100th power, that's the x that I'm putting into the ln. Anybody know what that's equal to? That's equal to 100. Now, e to the 100th power as like an actual number is what kind of a number? It's enormous, right? Probably more than like the number of atoms in the universe. I mean, like it's an enormous thing. I'm just making that up, but like it's huge. I mean, there's no point typing it in the calculator. I don't think. What is it? Times 10 to the 43rd? E to the 100 is on the order of 10 to the 43rd. So a 1 followed by 43 zeros. If you go that far to the right on our graph, you get up to 100. Yeah. So it grows to infinity very, very slowly. We're going to skip over 9. I'd ask you to fill in some of these properties later, but we did talk a bit about some of the things that we just noticed about that graph. We're going to fill in some of the properties here in number 10. Okay, let's see. Log of a times b. Anybody remember what happens when you have log of a product of two things? You add them, so it becomes log of a plus log of b. What happens to division? Subtraction, log a minus log b. These properties were useful way back when logs were invented a few hundred years ago when we didn't have a calculator. These properties are not all that important to us today, but part C is. what can you do when you have log of something to a power? You can bring that power down. We're going to use that property over and over again. And then ln of e to the x is just x. We're going to use that property as well. And then e to the ln of x is also x. Okay, so when we're ready, we jump to the next page. Just one quick observation, log of a plus b, if you see it, don't do anything with it. There's no, it's not in that list. I'm just pointing out that a plus b is not in our list. There's an a times b, there's an a over b, there's an a to a power. There is no property for log of a plus b. Okay, so this is something that is review. I think a lot of us know it already, but if you're trying to solve an equation and the unknown is in the exponent, that's when we use logs. And so for the first time, let's see if we can solve an equation where the variable is up in the power there. So we're trying to find t. By the way, this looks an awful lot like some financial word problem setup, right? What's the principle? Start with $100, interest rate 1%, maybe monthly because there's a 12 up there. And we want to know how long does it take to grow to 200. It's a doubling time. So this actually comes from something reasonable that you might be interested in solving. So what do we do first? Log? Yeah, we divide by that 100. So don't get antsy. The t is in the exponent, so we are using logs, but first you got to get that exponential piece by itself. So divide everything by 100. And we get 2 equals 1.01 to the 12t. And now we get to use this new tool. So we're going to take the log of both sides. And when I say log, I'm almost always going to mean ln. Doesn't matter at all. You could take log base 17 if you wanted. The reason that we use log and ln is because we have two buttons on our calculator that say those two things. And the reason that I'm going to use ln almost exclusively is because we're in calculus. And ln is the log of choice in calculus. Okay, and so ln of 2 is a number. Let's hold off on typing it in for just a moment. What can I do on the right-hand side? I can bring that exponent down. That's the important property for us. So if you have a power inside of a log, you can bring it right down in the front. So this is ln of 2, which is just some number, equals, and then down in the front, what do we put? 12t, ln of 1.01. I'll put a time symbol after the t just so we're really clear it's multiplication. And you can solve this for t in one shot. What do I do to both sides to solve for t? I divide by 12, ln 1.01, right? Divide by everything that isn't the t. So this needs to go away, and so does that. Just divide by both in one shot. So this is our answer. ln of 2 over 12 ln of 1.01. We'll type it in. ln of 2 divided by 12 ln of 1.01. Good. This is okay. It's wrong. It's wrong. You've got to be really careful when you're typing in fractions on the calculator. It doesn't understand what's on the bottom. So I hit enter. Turns out I get the wrong answer. I don't know if I'll recognize that that's an absurd answer for this problem, but it's real easy to make that mistake when you're typing it in. So we insert parentheses right there. Parentheses around the bottom. So this is the answer. And in the scope of this word problem, it takes about 5.8 years for the money to grow from $100 to $200. Any questions on that one? I'm just going to give you one quick alternative, just very briefly here. When we took ln of both sides, this bottom green line here, What did we bring down to the front? 12t. What did we really want to bring down? We really wanted the t, right? That's why we took the log, was to bring the t down. You're not obligated to take the 12 down. So if instead you said, okay, I'm just going to be really efficient here and just pick and choose what comes down, then we get that. Yes?
That works.
Absolutely.
Why are you the first person to tell me that?
You should probably ask the other people that didn't tell you. So why does it work? It works because 1.01 to the 12t is really the same as 1.01 to the 12 to the t. And so I'm thinking of the t as the only power. And then what would you do to both sides to solve for t? Divide by ln of 1.01 to the 12. So if you feel like that's cleaner, then go with that. You can do it either way, anytime. Ln of 1.01 to the 12. And in my head, 5.8. Yeah. That works. Look, it works. All right. So that one's good. Let's try this one down here at 14. Got some messy numbers, but we can handle that. It says in July 2000, Massachusetts' population was a little over 6 million. And then in July 2007, it was a little higher. So first, it says assuming exponential growth, write an equation that models the population t years after July of 2000. Okay, so let's just refresh our memories on our basic equation for exponential growth. I think it was something like P of t is equal to P0 times a to the t. I think that was our starting point for any exponential function. Am I using the right letters? Okay. All right, so let's think about this. The starting point here is July 2000, which very fortunately for us happens to match one of the data points. Do you guys remember what that gift represents in this problem? That's the P0. The initial population, P0, is the 6,300,000 and change. Okay, so that's easy enough. So P of t is equal to the 6,300,000 and change. And still times a to the t. And we still need to find the a, the base. Do you guys remember how do we use that other data point? What are we plugging for t? Yeah, t is 7 because 2007 is 7 years later. And what's the left-hand side? Is the other big number, 6,400,000. Okay, so let's plug those things in. And still trying to solve that mess for A. Are we first moving the 6.3 million or are we first moving the 7? Let's move that 6.3 million. So we'll divide both sides. And then to solve for A, is it logs? It's a radical. It's a root, it's not logs. We use logs when the variable is up there in the exponent. Here, it's the 7th power that we're trying to undo. And the opposite of a 7th power is a 7th root. Or what other power? 1/7. So I'm just gonna, I don't feel like writing everything again, so I'll cross that off. The 1/7, same as 7th root. And then we'll get this number on our calculator. Okay, so can somebody double check? Anybody get 1.0023? Great. Okay, I'm just going to store that number as A because I think we're going to be using it again. So just while it's there on my calculator, you hit that store button down there in the bottom left, and you hit the alpha key and then the green A, which is right below the alpha key. So 1.0023. All right, so then our final answer is P of t is this big number here in blue times 1.0023, and it was real close to a 5 there, wasn't it? Next numbers after 3 were like 4 and 8 or something. Yeah, okay, so that's probably pretty accurate. So we've got our exponential function. Good. And this function perfectly hits the 2 data points. It's going to give us the right population in 2000 and exactly the right population in 2007. Doesn't mean the population in between in real life is going to match the population of our graph, but hopefully it's pretty close. Okay, so let's use part B here. It says use the model to predict population for July 2008. It's kind of funny to predict that because it's in the past, but what value is t? It's just 8. Again, it's convenient because July was our starting point and we're just going to be consistent here. So this problem is really asking for p of 8. And just in terms of typing this thing in, I'd really like us to be able to use the stored number that we've got. So what is p of 8? So we've got the starting population, and then we multiply it by, what do I multiply it by? A. We typed in, we called it A, and then raised to what power? To the 8th. So this is the most accurate answer the calculator can give us. And so I realize that some of us might be a little bit turned off by the messiness of all these numbers, but it is what it is. I mean, we should be able to, with care and taking our time, type all these numbers in and get accurate answers. So just be deliberate as you type all these numbers in. Probably if I was on the ball, I would have stored the 6,300,000. I probably should have stored the initial population, maybe call it P or something, because it feels like we use that a few times too. All right, so that's our answer there, 6,483,104. Any questions so far? Okay, and then it says that in part C, it says the actual population in July 08 was this number. And so we can then see how far off our model was. So we're trying to compare the number we just wrote in purple with this number in black in the problem. So percent error, it's actually one that you guys, I think, used in on the exponential project, the population project. So to find the percent error, what am I doing? There are actually a few different ways, so different formulas from different people on that project. Okay, so we're going to subtract those two things. So we'll do the 6,483,104. That was our prediction. And then we'll subtract the actual answer, which is right up above. And once we have the difference, what do? We divide by the actual answer. Yeah, 6,497. You always want to compare it to the right answer, not to your prediction. Got to put the correct number down there. And if you feel like it, multiply by 100, so it really looks like a percent. Okay, so again, lots of care as we type all these things in. Put it over here. Okay, so because I see that number twice, I'm just going to store it right now, the right number, 6,497. But before I do that, what should I store? the number that I have right here. Like this is the only moment I have that number in the little short-term memory of the calculator. So we're going to store this guy as, I don't know, we'll call this one G for our guess for the population. So we made our guess, it was that. And then I want to store the right answer. So that's the one that was given in the problem. So how about I store this one for, as R for right answer, alpha R. So G is my guess, R is the right answer. In terms of those letters, what am I really typing in for this percent error? So G minus R, we did our guess, I subtracted the right answer, and then divide by which one? Divide by the right answer, R. Also good. Yeah, some folks use that formula on the project. You take your guess, divide it by the right answer, and then subtract 1. Same thing, and then I'll multiply by 100. So our percent error here was, so is that 22%? No, that's 0.2%. We've already hit it with the 100. So that's a pretty small error. Our model was quite accurate in terms of predicting this population in 2008. So this is about negative 0.229%. It's small. Okay, and again, part of the reason I want us to do this problem is so that we just get a little more practice with dealing with messy numbers on the calculator. And it's you can make your life easier by using that store button. So that's sort of part of why I wanted to do something with ugly numbers in it. All right, and then the last one here says, when will the population reach 7 million? Okay, so what are we doing here for the population to reach 7 million? So here in, I'll highlight in green. So this is my formula for everything. What do I do with this if I want to know when the population is 7 million? Make it equal 7 million. That's right. So this one right here, 7 million, is supposed to equal that whole thing. All right, and I'm kind of tired of writing all these numbers down, so how about we just start calling them the letters that we're going to use on the calculator anyway. I'm going to go ahead and call this the starting population. I'll call it P for population. It's a starting one. And the 7 million, it's fair enough to just write, I'll just write 7 million. And then did we have a letter for this thing in the parentheses? That was A, wasn't it? This thing right here was A. So, all right, so we got 7 million. 7 million is equal to P times A to the T. But now it feels like we've got a lot of unknowns, but we don't. We're just renaming the messy constants. What's the only unknown in the green equation? Is T. So we're trying to find T. So what do we do to both sides to solve for T? We need to move the P or the A first. Which one? We've got to divide by the P. So we get 7 million divided by the P. And then what do we do to solve for T? Yeah, the T is in the exponent. That's how you decide what to do. Look for where the variable is. It's in the exponent. We take the log of both sides. So we get 7 million over P, A to the T. I'm just writing it again so that I can put an ln in front of both sides. On the right-hand side, what can we do? Bring that T down. That was the goal. So we get T, ln of A, ln of all this stuff. We just copy. And then finally, to solve for T, divide by ln of A. ln of 7 million over p divided by ln of a is equal to the t that we're interested in. And if playing this game with the letters in there instead of the numbers makes you a little bit uncomfortable, that's okay. It's okay to be a little bit uncomfortable. The next time you do it, you'll be a little less uncomfortable. All right, so let's just see if we can get a number from all of this mess. So I think I still need to store something that I haven't done yet. I guess this guy right here I need to call P. So let's do that, 6362583. So that's going to be called P. And do we have anything else we needed to store? I think that was it, right? A is in there, P is in there. Okay, so then we are ready to type in this thing in one shot. But I promised you it's going to be a lot less messy typing it in with the A and the P than retyping all those actual numbers. So here we go, ln of 7 million. Okay, so you could hit the 0 6 times. Anybody know the shortcut for? All right, so times 10 to the 6 is a little bit better than hitting 6 zeros. And see this yellow E here? Second E. I don't know why it says EE, but then it shows you only one E, but that's 7 million right there. 7E6. So if you're doing any science class this semester, that's the scientific notation button right there. 7 times 10 to the 6. Okay, this guy gets divided by what? P. So we're dividing by alpha P. Where'd it go? There. And then the whole thing is divided by ln A. Alpha A. And that is a very compact way to deal with something that actually has quite a few big, messy numbers in it. And it turns out it's going to take about 40.7 years for Massachusetts population to reach 7 million, according to this prediction. So 2040, it says figure out the month. You guys could do the month, right? 0.7, 7th month? Well, good. I'm glad you guys were so upset about that. That was a good reaction. Right, so 0.7 is 7/10 of the way into the year. It's probably easier when the calendar had 10 months in it, because then 0.7 would be 7th month. Okay, so that is that. So here's what you guys are going to do. We have about 7 minutes or so. Right here, I believe there are 4 different examples, like little word problems with formulas attached to them. And so what you're going to do is you're going to take a look at the formula and the word problem. You're going to explain in English what the inverse function represents. What does the English inverse function represent? For the answers to those things, you are probably going to have the form given blah blah, this function outputs blah blah. And then you're going to find the equation for its inverse. Again, swapping the x and y was the first problem we did today. There are answers on the back. See how far you guys can get on these.